Okay, so since this already 11, I think we should get started. So for those who just joined, I'm just giving you a link where you can do mid-semester review because we're getting close to our mid-semester, right? So next week is the spring break. And then after that, we're gonna have the exam two, okay? So I think now is probably a good time to review or to give some comments regarding this class. Okay, so I can try to add in some of your, consider some of your comments, and then I can implement them in the second half of the semester. All right. Um, so, um, so for this class, we're going to continue on the drinking water treatment, and hopefully we can get this chapter finished in this class. Okay. Um, so if we again do a quick recap of our last class. So last class, we gave some definitions about the water treatment or drinking water treatment, right? So before we treat the water quality, we need to consider where the water is coming from, right? It can be surface water or it can be groundwater. And also we have a few water standards for the water treatment, right? So for example, we have the MCL, which is the maximum contaminant level, and the MCLG is the maximum contaminant level goal. Okay, so for these two, the major difference is that the MCL is for some contaminants that has a known toxicology effect, right? We know that they're toxic to humans, so we have to reinforce that standard. So for the MCLG, that's the goal, right? So it means that we're not very clear about its toxic effects. We're just implementing this for the sake of humans' health, right? We don't know what is the effect for now or for sure. Okay, so there may be some chronic effect or there may be no effect at all, but this is just for safe. And in terms of the methods to remove these contaminants, we said that there are screening, right? Screening is quite easy to achieve. We just add mesh to remove the larger chunks of the pollutants in the water, right? We specifically talk about the coagulation and flocculation. So coagulation and flocculation is mainly used for removing the colloids, right? So colloids are just like the milk, right? So these are suspended particles that are very small for them to settle down. So we add in coagulants into the colloid suspension to form larger particles. And then these larger particles can can coagulate with each other to form flocks, right? So basically we form larger particles at the beginning, and then these larger particles will form those branched structures. So we call these as flocks. So because of that, we need to consider which process needs to happen really fast and which process need to be very slow. So for coagulation, what we want is we want the rapid suspension of the coagulants. So that's why we will use turbines that has very large velocity gradients, right? So we show that if we assume that the turbine has a radius of 1 meter, then the maximum velocity can reach to 1 kilometer per second, which is very fast. So this is going to be beneficial if we want to mix the coagulants well with the polluted water. So for flocculation, since we're forming these very large particles, we don't want a very large speed because we may easily break these particles apart, right, to form smaller particles again. That's what we don't want. So that's why we're going to use a slower turbine, right? We use the paddles that has very small velocities or very peaceful rotation, or we just don't use any of these paddle at all. We just use channels, right? To just let the water to go by itself. So after a sufficient long suspension time, then we can remove these contaminants. So now this class, we're going to continue on the next stage regarding the water treatment. So if you just look at this diagram again to recall what is happening. So we have talked about the screening, the coagulation and flocculation. So the next stop is the sedimentation, right? So sedimentation basically means that the particles are large enough. So when they are introduced into a pool, right? When they're introduced into a basin, what happens is that because of their gravity, they're going to settle down, right? So the larger the particle, the faster the settling, or the faster the sedimentation. Okay, so at the end of the basin, what happens is if the particles go this way, or if they reach to this side, right? And then the water, because the water flow is the only outlet is at here, right, at the top. So because of that, the water is going to flow up and then bring all the unsettled particles to the outlet. So from this process, you can see that basically the sedimentation basin will only remove particles that are large enough, or we will only remove particles that has a settling velocity that's higher than a critical value. Okay, so if you want to know what is this critical velocity here, then that is going to be the particle that has a trajectory that goes towards here. Right, so it's going to flow diagonally from the top to the bottom corner. And then if the particles are larger than this size, then what that means is that it can settle down faster to settle down to the basin. Okay, so if the particles are too small, then they cannot settle down. And then what happens is that they're going to flow with the water flow to come out. Okay, so then it comes a pretty interesting question. So how do we design this basin here? Or how do we calculate this critical velocity, right? So an easier way is to just analyze the trajectory or the force balance, okay? Or not the force balance, but just analyze how the particles are flowing in this basin. So here I'm drawing this this sedimentation basin again. So this is showing a cross-sectional review. So the actual shape looks like this, okay? So it's going to be a rectangular shape, right? And then we can further assume that this is the length, right? If we look at this way, this is the length of the basin, this is the height of the basin, right? And here you have the width of the basin, okay? So if we want to consider the critical velocity, then that's going to be the particle that flows from here all the way here, flow diagonally, right? And then if we assume that this particle that has the critical velocity of V0, okay? So what happens is that after a residence time, then this particle is going to settle down exactly the height of this sedimentation basin, okay? So that's going to be equal to H. So this is how the this critical velocity is related to the time and the dimension or the geometry of this basin here. Okay, so further, we know that basically this critical velocity is calculated by h divided by t. Okay, so similar to what has been written here. Okay, so what about the time? So how do we solve for time? So time is the retention time or the residence time of the particles. Okay, so the residence time is related to the volume of the basin divided by the flow rate. Okay, so it's the volume of this reactor divided by the flow rate of the reactor. This is a way to estimate what is the average residence time or the retention time of the particle. So now we can plug this in. So basically we have V0 equal to H divided by T, and that's going to be H multiplied by Q divided by V, okay? So further, if you look at the volume, since this is cubic, right, or rectangular, so V is going to be equal to L multiplied by H multiplied by W, okay? So basically you can plug this term into here, and this is what we get, okay? HQ divided by LHW. So you can cancel the H here, you get Q divided by L multiplied by W, okay? So further, if you look at L multiplied by W, that's just the length multiplied by the width of this reactor. So that is going to be the area of this reactor, okay? So just the top area of the reactor, okay? So basically you can, what you can get is this critical velocity is just the flow rate through this sedimentation basin divided by the surface area of this sedimentation basin, okay? So basically what's happening in the water treatment facility is that when they build up this sedimentation basin, what people do is they will select a critical velocity. So people also call this critical velocity as the overflow rate, okay? So they will designate a overflow rate, let's say V0, okay? Let's say we just set it as let's say 1 meter per day. Okay, so this is the critical velocity, right? Or the overflow rate. And then they can, based on this overflow rate, to design their sedimentation basin. Okay, so what happens is for this water treatment facility, they would know what is the general flow rate through this basin, right? So basically, if you know the flow rate, then you can just calculate what is the area that's required by this sedimentation basin here. Okay, so what I mean is that if you want to design this, let's say this reactor or this sedimentation basin, you need to know what is dimension. But what determines the dimension? It is actually the flow rate of the water that's to be treated and this overflow rate. Okay, so here I have a example problem. I think this is also one of your homework problems. So maybe we can spend just 1 minute for you to go over this problem, and then we can talk about this. All right. Okay, so let's look at this problem together. All right. So what this problem is saying is that we have a basically a water treatment plant that is processing the water flow at this flow rate. Okay, so it's 1 meters cubed per second. Okay, so it's using 10 sedimentation basins to remove the larger particles. All right, and then we designate a overflow rate of 15 meters cube per day per square meter. Okay, so this is actually a velocity. Okay, so don't be scared for its unit here. So basically, this is just a meter per day unit here. Okay, so it's asking what should be the surface area of each tank. Okay, so if you know the relationship between the overflow rate and the design parameters for this water treatment plant, then you should know that the area should just be equal to Q divided by V0, right? The flow rate divided by the overflow rate. So that's going to be 1 meters cubed per second divided by 15 meters per day. Okay, so based on this, you can calculate what is the total area, what is the total surface area for the sedimentation basin. So you should also pay attention that 1 day is basically 24 hours multiplied by 3,600 seconds. Okay, so remember to do that conversion here. So basically, you can calculate the total area for this sedimentation basin. All right, and then since it's designing 10 of them, so the area for each tank or for each sedimentation basin is just a total divided by 10. Okay, so this is going to be the solution for this problem. So we should use this simple relationship where the area is equal to the flow rate divided by the overflow rate, or the overflow rate is equal to, basically overflow rate is equal to the flow rate of water divided by the area of the sedimentation basin. Okay, so this is the general concept in terms of the designing for these this device. Okay. So further, if we look at our next stop, okay, after the sedimentation basin, then basically we remove the larger particles from here, right? And for the very small particles, we're going to introduce them into a sand filtration or a sand filter. Then you may wonder, why can't we just use one sedimentation basin? Isn't this enough? So this is actually not enough because as we said, only large particles can get removed, but there are very small, there are a lot of very small particles. For example, the dead bacteria, right? Or maybe they're alive because we had this pre-chlorination here. So if they're dead, then these bacteria are just going to be around 1 micrometer, which are still very small for us to completely remove them by gravity. Okay, so that's why we have to introduce them into a sand filter. And an interesting fact is that the sand filter has been in these water treatment for, I would say, more than hundreds of years. So if you recall, when we talk about the history for the water treatment, everything started from UK, right? So at that time, in order to treat the water quality from the Thames River, so what they did is they built a sand filter. So basically, they just collect some sand, right? And then for their branch of water where they take the water out, they'll build that something like a dam. Okay, so you just collect some sand in there, and then the sand is going to filter out the suspended particles inside. So what you get out of it is going to be the purified water. Okay, so the sand filtration has been a common concept for water treatment for quite a long time. Okay, so I would say people are very familiar with how it works. So here, what I'm showing is a schematic diagram of this sand filter here. In nowadays, when people design these sand filters, they would use multiple layers of materials. So for example, here is the water to be treated. Okay, so what happens is that people actually would set up this sand layer. Okay, so basically, this sand layer here is going to remove those suspended particles from the water. Okay, but further below the sand layer, people also build this support gravel. So this is mainly to support this sand layer because you don't want any water to come out of you don't want any sand particles to flow with water, right? So just imagine if we don't have this support here, then after the water is filtered, then you, of course, you're going to have some sand particles flowing with the under drain. Okay, so flow with the purified water here. So the support gravel is mainly for supporting these sand layers here. So in terms of the detailed mechanism or detailed principle for removing the pollutants, there are several of them. So you can have the straining. So basically the straining means that the particles are too large. For example, here, although we're filtering out smaller particles, but the size may be comparable to the sand particles, right? So mainly it's just that these particles are too large that there's no way it can flow through the channel here, right? So it's getting blocked. So there can also be interception. So what interception means is that the particles are quite small, but its size is still not negligible. So what happens is their surface may get contact with the surface of the sand particles, and then because of the van der Waals force, is basically attracted or attached onto the sand surface. And then you're going to get this collection here. Although this particle can flow through the channel, but it's still getting collected or it's still getting attached onto the sand particle. Okay, so we can also have the flocculation. So what flocculation means is the particles are blocking itself. Okay, so you have a particle that's attached onto the surface, or maybe before they attach, the particles can attach to each other. So basically forming larger particles, and then they're getting trapped in the sand filter. And finally, you can have the sedimentation, which is because of the gravity, you can just get collected onto the sand filter. So there are different mechanisms for people to remove these smaller particles, right? Um, so what happens is that during the filtration process, so initially the particles are retained on the top layers, right? You can, as you can imagine, the particles are getting collected on the top layers. But after some time, then what you can imagine is that the layers, the top layers kinds of filled by the particles. And then the opening channels for the water to flow by is also going to reduce, right? So that's going to increase the velocity of the water through the top layer of the sand filter, right? So if the water velocity becomes higher, it's going to break the particles and force these particles to move down. Okay, so basically it's flushing these smaller particles further deeper in this sand layer. But there should be a limit, right? So when basically if the velocity is too large or basically the sand filter is saturated, then what happens is the water or the contaminants are going to penetrate the media. So when that happens, the effluent, basically the outlet flow, is going to become more turbid. Okay, so the turbidity is going to increase. So of course, this is a situation that people don't want, because what this means is that the basically the filter is damaged, right? So we're leaking all of these pollutants out of the water, out of the sand filter. So before that happens, people would use the backwashing. So what happens is we can inject water back into the sand filter. So that's going to flush the contaminants away. Okay, so we can have a collector that basically collects these flushed water, right, and then remove these collected particles. But still, I would say the sand filtration, after some time, people have to stop it and then replace the sand, because there are some smaller particles that there's no way for us to remove these contaminants just by flushing the water backwards, right? And because of this feature here, as you can imagine, there are some parameters that are quite important for the design of the filter, right? So this parameter is called the loading rate. So people also call this as the phase velocity. Okay, so you can imagine it as the average velocity of water going perpendicular towards this sand layer here. Okay, so the way it's defined is as is calculated by the flow rate divided by the surface area of the sand layer. Okay, it looks quite similar to the sedimentation basin, right? So we introduced that the overflow rate is equal to the flow rate divided by the surface area of the sedimentation basin. So it is the same here. So the loading rate for the sand filter is calculated by the flow rate divided by the area of this sand layer. Okay, so you can see that this is going to yield a parameter that has the unit of meter per second. Okay, so this is also a velocity, kinds of a velocity. So that's why we also call it as the phase velocity. So now if I ask you a question, let's say we're trying to generate the same, or trying to filter the same amount of water. Okay, so let's say the water flow rate is 1 cubic meter per second. And here we have two sand filters. Okay, so one has a larger surface area and the other has a smaller surface area. Okay, so which one should people use, or just based on our instinct, right? So since I didn't set up a quiz question, so you can type in your answer from the chat. Okay, let's call this first type as A and the second type as B. So which type do you prefer? Okay, yeah, I think all of you get the correct answer. All right, so we would prefer this first one, mainly because this one is going to have a smaller loading rate or a smaller velocity, right? If it has a smaller velocity, then basically we can remove them more efficiently. The water is going to stay for a longer time, right? And then because the residence time increases, then we're going to have more sufficient time to remove these pollutants, right? And also, since we have a larger area, basically larger volume of the sand, then this filter can last for a longer time, right? So we would prefer this one, but in a mathematical way, what that means is we have the same flow rate here. We're increasing the surface area of the sand filter, which reduces the loading rate of the water treatment. So we prefer a smaller loading rate. So that's why for the when people design these sand filters, they would set up a maximum loading rate. So there's no way the flow rate can be higher than that maximum loading rate. Okay. So basically, for different types of the sand filter, right now we're going to just learn two types. So one of them is the single media rapid filter. So for this filter, it's just going to have the very simple design. We have the super gravel at the bottom, and then you have a layer of sand. So this is a single media, which means that the sand here are going to have the uniform sizes, okay, or similar sizes. All right. So that's why for this type of filter, people would designate a maximum loading rate. So basically the maximum V0 or the VA here, okay? So people say that the loading rate or the phase velocity cannot be further higher compared to this one. If it's higher than this one, then you have to build more of these sand filters, okay? We cannot allow the flow rate or the loading rate to be higher than this value here. So there are other design considerations too. So basically, when people design these rapid sand filters or single media rapid sand filter, we need to build at least 4 units. Okay, so I think this is mainly to consider the scenario where you have to replace the sand, which basically means that you have to take it offline. Okay, so this would give you enough of the, let's say, the space of safety, right? You don't want all of them to be taken offline, because if that's the case, you cannot generate any purified water anymore, right? And each of the unit will have a area or the surface area up to 100 meters cube, okay? So if you have a further larger area, the issue is the water will not distribute uniformly, right? If you have a very large sand filter, then water might be just filtering from one side, not the other side. Okay, so that's why we also set up a maximum area for this sand filter. And as we introduced, we can have the backwashing to remove these pollutants, right? To just flush some water back and then remove the larger particles. So you can pump the water back through the media, so the particles are getting removed. So in terms of the backwash, it's going to use 2 to 4% of the treated water. So you can just take around 2 to 4% of the water from here and then just flush it back, okay? So this is a single media rapid sand filter, okay? So we can also have the multimedia. So you see that for this single media, what happens is, if you consider the particle removal in this sand layer here, so you can imagine that basically the larger particles are first getting removed at the top, okay? So after some time of collection, then this top layer is getting heavier and heavier because you're mainly collecting larger particles, while the smaller particles can penetrate deeper. So what happens is that you're going to have a top that weighs much heavier compared to the bottom. So that's very easy to break this sand layer apart. So that's why people imagine, why can't we design a filter that has multiple layers? So for example, we can have a layer that has much lighter weight on the top, right? So we can have larger pore sizes on the top so that we can block the larger particles, while the lower layer are going to have a smaller pore size, which weighs heavier compared to the top layer. So that's going to be more stable in terms of the filter media. So this is actually the design for this multimedia filter here. So the multimedia filter, what that means is that we're going to use several media, including the sand, anthracite. So anthracite is, you can regard it as the basically larger grains of sand, but it's also lighter compared to sand. Okay, so you can include garnet or some other media. Okay, what we are going to do is we're going to place the largest and lightest on the top, so we can remove the larger particles more efficiently from the top, right? So that it doesn't weigh heavier compared to the lower layer. So it's also going to be more stable in terms of the filter media structure here, right? So what happens is it's going to reduce the resistance and increase the capacity, because you can use this larger anthracite media. And also because of that, you can now use a much higher, or I wouldn't say much higher, but it's comparatively higher loading rate compared to the single media rapid sand filter box. Okay, so if you compare, this one can go up to 300 meters cubed per day per meter squared, right? And for the single media, the maximum loading rate is 235. Okay, so by using the multimedia, we can have a higher velocity, or basically a higher loading rate for the water filtration. So we can also use the backwash. So for the backwash, we'll normally use the air and water mixture. So if you recall, for the single media, we use water only because this is quite simple, right? So for the multimedia, normally this layer is going to become much thicker. So if you have a thicker layer, you're going to inject more water into the media, right? So that's why we can introduce some air bubbles here. So air bubbles are lighter, so they can rise up more rapidly to remove the contaminants. Okay, so for the multimedia filter, we're going to use the air water mixture to clean that up. So finally, it's the design considerations again. So here, this class, we are going to go over quite many design considerations. Okay, so for the design of the rapid sand filter, what happens is people would use even number of filters because it's more convenient for building up, right? By having these even numbers, what that also means is that if one is offline, right, the other one can still be in the running state. You don't have the trouble of cutting off the water if you want to take one sand filter offline. Okay, so further, for the single media rapid sand filter, people also use at least 4 sandboxes, at least 4 filters, right? So people also will guarantee that the filter loading rate, or that VA value, should not be higher than the maximum loading rate. So if you recall, for the single sand filter there, the maximum loading rate is 235. While for the multimedia, that's 300. Okay, so we always need to do a sanity check to make sure that our design loading rate is smaller than that value, right? So here I have a simple example here. I think this is also one of your homework problem. So basically, it's asking, let's say you have a water to be processed, right? And then its flow rate is 0.8 meters cubed per second. It's asking us how many rapid sand filter boxes are needed for a loading rate of 100 meters cubed per day per meter square. Okay, so basically, if you have these 2 conditions, one is the flow rate, one is the loading rate, then you can calculate what is the surface area. Okay, so if you go back to this equation again, so basically the loading rate is defined as the flow rate divided by the area of the filter, right? So if you rearrange it, then the area of the filter is going to be the flow rate divided by the loading rate. Okay, so let's maybe spend another minute to look at this problem again. I think I need to charge my pen here before I write anything onto the board here. Okay. So if you can get these numbers down, I'll stop the sharing for a little bit, and then I'll connect back online. Okay, so let's look at this problem, all right? So basically, this problem tells us what is the flow rate and what is the loading rate, right? It's asking us how many of these rapid sand filter boxes that has this type of dimension we need, okay? So first, based on the definition of the loading rate, right? So VA is equal to Q divided by the surface area of the sandbox, okay? So we can rearrange it and get AS is equal to Q divided by VA, which is 0.8 meters cubed per second divided by 110 meters cubed per day per square meter. Okay, so we can cancel this meter here and then just get the days. All right, and then further, we should notice that the day here, it cannot directly cancel with second. Okay, so 1 day is equal to 24 multiplied by 3,600 seconds. Okay, so more specifically, I would say that a more easier way is to convert this flow rate into days. So basically, the flow rate is 0.8 meters cubed per second multiplied by 24 multiplied by 3,600 seconds per day. And you can find out that this flow rate is 69,120 meters cubed per day. Okay, so this is the total flow rate of the water through this sand filter box here. Okay, so if you further plug this in here, you can find out that the area that's required is it's 628 meters squared. Okay, so this is the area, the surface area that's required for removing these particles here. So it's asking us how many of these sand filters do we need if we know that each of them has a 10 by 10 dimension, right? So basically, what people will do is they're going to separate these sand filters into different regions, right? We have 10 of them. So each of them are going to process some fraction of the water, right? And then to calculate what is number, we just need to divide this AS divide by the area of each sand filter box here, right? That's 10 by 10 meters squared. Basically, it's 628 divided by 100. You have 6.28 number of sand boxes that's required, okay? So this is the answer. So how do we deal with it, right? So can we build a sand filter that's just 0.28 of a single sand filter, right? Should we build half of it? No, right? We should round it up. So if we round it up, we're going to get 7. So the reason why we're not rounding it down is because if we just build 6 of them, then the velocity or the loading rate will become higher. So basically that's not sufficient to remove the contaminants from the water, right? So we always need to round up. I'll say always round up. Okay, so this is no matter whether that's 6.28 or 6.01. Even if it's 6.01, we should still round it up just to be safe, right? If it's lower than the required number of sand filters, then the loading rate will be higher than the design value, which means that it's going to be more dangerous if we use a smaller number. So if we round it up, we get 7, right? So if you look at the design criteria, we should use an even number of filters. So we need to further increase it to 8, okay? So basically this will satisfy the requirement that we have 8 number of the sand filter. We have an even number of the sand filters, okay? So this is in terms of the practical design for the sand filters, all right? So if you think back, we discussed the sedimentation basin, right? It's using the, basically it's using the same set of equations. So VA is equal to Q divided by the area of the sedimentation basin, right? So this is for sedimentation. Well, for the sand filters, we have the V0 equal to Q divided by A. I think this is 0 and this is A here, right? That's the flow rate divided by the surface area of the sand filter. So further, if you know what is the dimension of each sand filter, you can calculate how many sand filters do you need, okay? So this is a design considerations for the sand filter. So we're going to use the rest of the time to discuss the softening, okay, the hardness of the water. So basically, when we discuss the hardness of the water, we're talking about these white scales or the suspensions when we boil the water from a kettle. Okay, so this is quite troublesome for a lot of the households because I think you probably have the experience that after some time of using the faucet water, the flow rate is getting smaller and smaller until it's just dripping, even if you open it to the maximum, right? This is because of the hardness of the water. That's because you're getting a lot of these white scales in the water pipes, mainly because we're living in Rolla, we're using the underground water, right? We're using the well water, which contains a lot of the calcium and magnesium ions, okay? So actually for the hardness of water, it's not only these ions. So a lot of these ions can also form white scales, can form sedimentations. So if we want to calculate the total hardness of the water, then what people do is actually can find out what is the concentration in mole per liter. Okay, so basically sum up all the molarity of these ions together to get the total hardness. Or the TH here. So the total hardness is just the molar, the summation of all the molarity for these ions. And if you notice, these ions are polyvalent, right? We don't have any cations that has, let's say, just single charge here, because for these ions, they are soluble in water, right? They won't form these white scales. They won't form these sedimentations. So basically, whenever people calculate the total hardness of the water, they're going to sum up all of these ions together, okay? So another common way that people represent the total hardness is to represent this value in milligram as calcium carbonate, okay? So you may ask the question why we're using this equivalent mass again, right? So we were using this equivalent mass concentration when we were talking about the alkalinity. So I think this caused some trouble in your exam one, okay? So when you're trying to calculate or convert it into the equivalent mass. But why are we using the equivalent mass again when we're talking about the hardness? I would say that this has a more engineering purpose. This is because as we have talked about, so this hardness is mainly because of the calcium bicarbonate or the magnesium bicarbonate, right? So people can measure what is the concentration of these bicarbonate ions. Okay, so let's say that we find out that this concentration here is 0.1 mole per liter. Okay, so this is the concentration of the bicarbonate ion. So how do we deal with these carbonate ions? So the method people do is they're going to purchase the calcium carbonate, which is just limestone. These are very cheap from the mines, right? And then they're going to bake it. Under high temperature, this is going to change into calcium oxide. And when you dissolve them into water, let's say just throw them into the treated water here, they're going to form calcium hydroxide, okay? So what happens is that for each number of the calcium bicarbonate, it's going to react with one number of the calcium hydroxide. All right, so that's going to form two number of the calcium carbonate. Okay, and then you have what you have the water, and then you have Basically, you just have water here. Okay, 2 number of calcium carbonate and 2 number of water. Okay, so this is the reaction here. And now you can try to understand why we're using this equivalent mass. So basically, if you know what is the concentration of the bicarbonate ion, so that's going to react with one number of the calcium hydroxide. So one number of calcium hydroxide would correspond to one number of the calcium carbonate. Okay, so now let's say the water treatment company knows what is the hardness of the water, right? And they can directly call the company which sell these calcium carbonate. Let's say you just give me 1 ton of the calcium carbonate, right? If you represent them in the concentration of the calcium carbonate. So that's why I would prefer to use this equivalent mass concentration in here, right? To calculate what is the hardness of water, right? So the hardness of water is important for the household. It's also important for the power plants. We know that the power plants use these high temperature steams. So we have to heat this water into very high temperature. So if we send the water that has a very high hardness, then basically they're going to block these tubes, right? And then you may have explosion because of the sedimentation, because of these white scales here. So for the, I would say for the power plants, they would prefer to use ultra pure water, which it doesn't have any of these polyvalent ions in the water, okay? So I think, let's see, we can probably use the last 2 minutes to go over this question here. So basically, when people calculate the total hardness, although we can use this equation here to calculate all of these polyvalent ions, but you can find out that the major ions or the most concentrated ions are still calcium and magnesium ions. So they are represented as the calcium carbonate in milligram per liter, okay? So normally a total hardness of 60 to 120, people would refer that as the moderately hard, okay? So if the total hardness is higher than this value here, then it's treated as hard water, okay? So further within the hardness, people divide them into the carbonate hardness. So basically the carbonate hardness is a species that contains carbonate species. So basically the bicarbonate, calcium bicarbonate or magnesium bicarbonate, they're categorized as the carbonate hardness, okay? So there can also be some non-carbonate hardness, okay? So these are, let's say, calcium sulfate or the calcium chloride, right? So for these species, when you heat it into high temperature, they're also going to form the scales. They're also going to form sedimentation. But for these hardness, it's quite difficult to remove them. So we're mainly dealing with the carbonate hardness, okay? So now you can see that basically the total hardness, you can further divide them into the carbonate hardness and non-carbonate hardness. Okay, so carbonate hardness is just species that's bonded with the bicarbonate ions, and the non-carbonate hardness are the species that's bonded with the sulfate or chloride ions. Okay, so finally is definition of the bar graph. So the bar graph basically is showing the cations and the anions in different bars. So to show what is the relationship between the carbonate hardness and the non-carbonate hardness. Okay, so you're going to have 1 or 2 example problem in your homework, and I think maybe we can talk about that in our next class. Okay, so that's all for this class, and let me know if you have any questions. All right.